So today's class will be taught by myself and Bouba jointly, and this class is useful when you are reporting the results or making any conclusions from your results. So things that we will cover, so robustness analysis, I will cover that first part, and then Bouba for the first time will be teaching in the summer school. We'll be covering, yes, for Bouba, and he will be covering statistical inference part, and then Mauricio will kindly go through the do file very shortly, just to show you how to do things in Stata. So the sources. Of course, the book is chapter 8, is on robustness analysis and statistical inferences. There is a paper by Sabina and Maria Santos, which is published at the World Development. There are some further robustness analysis if you are interested. And Yele Batana, I will present a figure from this paper. It's one of the first paper to do the dominance curves that I will be presenting, and it's also published in 2013. So the main questions that we would like to answer in these after this lecture is, of course, how accurate are the estimates? You get estimates, you get M0 or MPI is equal to 0.5. Or you get the value of multidimensional head count ratio. And the question is how accurate these estimates are. If they're used for policy, what is the chance that they are mistaken? And there are two kind of issues that we may be concerned with. One is how sensitive policy prescriptions are to the choices of parameters. You make different choices, right? You select weights, you select poverty cutoffs, you select deprivation cutoff, and then you may ask how robust my answers are subject to these different choices. And secondly, it's about the sample, because a question has been raised earlier in this class as well, that we do not compute the point estimates from census or population because we do not have all the relevant data, right? So most of the time we use sample, and so how accurate our estimates are based on the sample, because sample collects maybe less than 1% of the population, it may be less, okay? So based on the sample that has been drawn from the population, and then the estimates are supposed to represent the population parameter, and the question is how confident you are about your estimates, and Bouba will go through that part. Now, these are the kind of places or issues where you need to do robustness analysis or statistical inferences. A central government wants to allocate budget to poor according to the MPI in each region of the country. Of course, then you need to test if the regional comparisons are robust and statistically significant. Okay, because you are going to allocate more fund to one region compared to another. But you should be able to say confidently, yes, the region that we are saying should receive the fund is definitely poorer. Or a minister wants to show the steepest decrease in poverty in their region or dimensions. The first one is cross-sectional comparison, and the second one is more related to intertemporal comparisons. Has poverty gone down? Can you say confidently, yes, it has gone down with respect to different parameters, alternative choices of parameters, or based on the sample that you are using? Does it allow you to say that it has definitely gone down? Let us take an example using the global MPI data. So for k equal to 1/3, which is the poverty cutoff that is used for the global MPI reported in the Human Development Report, MPI for Zambia is larger than the MPI for Nigeria. So if you believe that the 1/3 cutoff is the right one for you, based on that, Zambia's MPI is larger than that of Nigeria's. These are used using older data sets, not the newest one, but just for the example. Now someone says, you know what, k equal to 1/3 I find is too mild. It probably k equal to half, 50% of weighted indicators. When we do the analysis, we find Nigeria is actually poorer than Zambia. So when you have a different choice of cutoffs, then things can, you know, be different, or the comparisons may reversed. So are there situations where we can say no matter which poverty line or no matter which poverty cutoff we choose, we are going to have larger poverty in one country than the other? Does it remind you something that we spoke in the first class, on the first day? Dominance analysis, exactly, stochastic dominance. Okay, it's very similar, and we'll present that. The other kind of issue that may arise is through, you know, your conclusions based on sample. Have a look at it. You have from there are examples of two pairs of Indian states. The first one is Goa and Punjab. Difference is 0.31 in their M0. Are you having trouble seeing? Okay. And then you have Maharashtra and Tripura, which has a difference of almost a similar extent. And as Bouba will present in the second half of this lecture, that one comparison is statistically significant. You can say confidently, yes, Punjab has a larger MPI than Goa. However, when we compare Tripura and Maharashtra, you will not be able to make such comparisons. These are just examples from Indian states. So that's why it is important. So it is not just important to compute your M0, which you have done until now, your multidimensional head count, break them down by subgroups, break them down by dimensions. It is also important to conduct proper robustness analysis, because when you are also presenting your results on Friday, you need to be able to say, yes, we have done this kind of robustness analysis and our analysis is robust to variation in parameters, or it's a complete robust comparison. We know for sure urban areas have lower poverty than rural areas, no matter which poverty cutoff we select. Or based on the samples we have tested, definitely it has gone down. And you can even combine, as we will just present, and you will see, you can combine the statistical inferences and dominance analysis and present a very robust comparisons. So for robustness analysis, you will see there are three major parameters in the computation of M0, right? You need to select weights, you need to select deprivation cutoffs, you need to select poverty cutoff. Do you all agree with me? Anything else you need to choose? Any other decisions? What are the decisions you need to make when you are computing the M0? Yes, please. Yes, I have mentioned that. Anything else apart from that? Indicators. Indicators definitions. Yes, I didn't mention that. It could be definitely. Choice of indicators. Exactly. Okay, dimensions. So there are various choices. So in this lecture today, in the first half, I will present two types of analysis, robustness analysis we do. The first is dominance analysis for changes with respect to the poverty cutoff, and it will be very similar to what I presented on the first day on dominance analysis. Remember, if we could say something about no matter what poverty line we choose, we should be able to say if poverty has gone down or gone up, or poverty in one region is higher than the other. It will be very similar to that. I'm not going to discuss too much on multidimensional dominance, because it will take much more time. At this moment, we do not have enough time to discuss multidimensional dominance. And the second one is rank robustness analysis. The main purpose of this rank robustness analysis is that you have different specifications. Suppose you have the initial set of parameters, the initial set of weights, initial set of deprivation cutoffs. And then you want to know, what if instead of this particular indicator, I select a second, another indicator. For example, instead of weight for age, you want to take height for age, or you want to take weight for height. What if I replace these indicators? You replace that indicator, you get a new set of MPI, and suppose across regions you are looking for regional ranking, you get a new set of ranking, you look at the correlation between them. Okay? So it's a rank correlation analysis. If you want to test if the ranks has changed or not, this kind of analysis you could do using rank correlation coefficient. However, if you also want to capture the level, whether how much the level has changed or not, you could also compute the general correlation, which is Pearson's correlation, that most of you know. It can be done in Stata by a command called CORR, correlation. So recall the unidimensional dominance that we had in our first class. When can we say that one distribution having unambiguously higher poverty than another distribution? Remember? Anyone?
When the discount ratio is greater than the other for every cutoff.
And when does that happen?
When it is always above 21.
Exactly. So one distribution lies above that of another distribution. So when you have two distributions like this, and one is always above another distribution, for example, the red distribution here is always above, it's nowhere below than the blue distribution. In that case, for the red distribution, you can never have lower poverty than the blue distribution, right? Whatever poverty line you select. Very well. Now, note there is a slight difference when we are, say, looking at the multidimensional case. In the multidimensional case, we also, when we are computing M0, we compute the deprivation score vector, right? Then we set the poverty cutoff and then identify. What is the main difference between income poverty analysis, where you use a poverty line and then we use the deprivation score and select a cutoff? Is there a difference? The idea is very similar. So in income poverty, we identify those who are below the poverty line. And for the multidimensional case, we identify whose deprivation score is lower or higher than K? Higher than K. So for income poverty analysis, we identify those as poor whose incomes fall below the poverty line. And in this case, we identify those whose deprivation scores lie on or above the poverty cutoff, right? Now, when we ask can we say that a distribution has higher multidimensional head count or adjusted head count ratio for any poverty cutoff, no matter what you select, for a given weight vector? And so suppose you are given with the weight vectors and the deprivation cutoffs. They are given to you at first. When can you say that a distribution has higher multidimensional head count and adjusted head count ratio, no matter which poverty cutoff you select? It's very much similar to the concept of unidimensional stochastic dominance, and the results, of course, comes from James's and Sabina and James's paper in Journal of Public Economics. So we consider the following deprivation matrix, which you have seen several times in previous classes. You have the deprivation score. So you suppose you are using equal weight, you just count the number of deprivations. First person has 0, second person has 2, third person has 4, fourth person has 1. The idea is that if a deprivation score vector C for a joint distribution X, so you have a matrix X and you compute the deprivation score vector C, first order stochastically dominates another deprivation score vector C prime, okay, from another achievement. So you have two achievement matrix X and X prime, you get two deprivation score vectors C and C prime. Then X has no higher H and M0 than X prime for all K, and X has strictly lower H and M0 for all K, okay. So this is the first order dominance that should give the result. So if one distribution first order dominates another distribution, then of course we have, you know, higher or lower H in 1, and M0 is actually a second order dominance. And if you recall, I mentioned that lower order dominance implies higher order dominance. So if you have first order dominance, it implies second, implies third, and so on. And H is actually a first order dominance. You compare the two distributions, you get H dominance, and H dominance implies M0 dominance, not the other way around though. So, given that I told you that subtle difference between income poverty and multidimensional poverty, in income poverty you identify those as poor whose income is less than the poverty line, and in multidimensional case you identify those as multidimensionally poor whose deprivation score is on or larger than the poverty cutoff. As a result, we need to define something called the complement of a cumulative distribution function, because we are looking at the other end of the distribution. And we call it complementary CDF. Sometimes people call from different branch as survival function, reliability function, with different names. But the main idea is that it is the complement of the CDF. So for CDF, you look people who has less than a particular point. Here you look people who has more than a particular point. And so if you have, say, two vectors, suppose C and C prime, please have a look. Can you select one poverty cutoff where you have larger poverty in C? At 2? Who has larger poverty at 2? Possible. So if you draw this answer, what you are having, you select a particular poverty cutoff, and the height is giving you the multidimensional head count ratio. So if you take k equal to 0, just k equal to 0, k equal to 0, how many people are poor in both distributions? All, right? Equal or larger. If you have, say, k equal to 0.5, how many of them are poor? In red? 0.5. One poor in the red distribution. If you have k equal to 0.5, that means you identify those with deprivation score, 3 of them. In distribution blue, all of them. So higher for this particular poverty cutoff. If you select a value, say, of 1.5, how many people do you identify in red? 2. In blue? You see, so you can never find a poverty cutoff where you are going to have higher poverty in the red distribution, because the blue distribution lie nowhere below the red distribution. So the blue distribution will always have at least as high as poverty as in the red distribution. Now, I am not going in details, which we explain in the book, that the area below these curves actually can give you, of course subject to a cutoff, can give you the value of M0. So for M0, you need to compute the area underneath the curve. That is explained in the book, but I am not going here in details. But just for your information, if we have this kind of situation, we know that one distribution has higher poverty than another distribution, no matter what cutoff you choose, okay? And this dominance implies dominance in terms of M0. So if you plot the M0s, suppose you have the cutoff and you plot all the M0s, I will show in the next example. If dominance holds here, dominance will hold in M0. However, the other way around is not true. So if you do not have dominance, you have crossings of these particular curves, then you can go and check if the M0 dominance are holding. But once you have one C vector lying above another C vector, you know for sure it has higher H and higher M0, no matter what poverty cutoff you choose. Okay, so when you are presenting your results and you say this region has higher poverty or rural area has higher poverty than urban area, We will just ask, and it's a fair question. Well, what if you choose another poverty cutoff? And if you just present this slide, you know what? We have checked, and it does not matter what poverty cutoff we choose. After we have selected the deprivation cutoff and the weight vector, it does not matter what poverty cutoff you choose. Rural areas always have higher poverty than urban areas. It's a strong result. Okay, but whatever I am talking here is all in terms of population. When you are doing it, when you have to make such a conclusive answer, always higher, always lower, and you are doing from the sample, you have to at least conduct some test. Okay, and Bouba will talk about those tests next. Question in this one? Is it clear? Please feel free to ask. I'm happy to go through. So this is the first order dominance, right? It's very same as the first order dominance that we discussed on the first day. So these are M0 curve, and these are taken from Yele-Batanos exercise. So if you see, he has plotted poverty cutoff on the horizontal axis, and M0, although it says M0 poverty rate, is actually the M0 values, the adjusted headcount ratio, the M0 values on the vertical axis. And he has plotted for all k. And you can clearly see one curve lies above the other. Now, had it been in terms of the population, if we had computed these things based on a population or a census, we did not have to do any robust or statistical analysis because dominance holds. However, given that it has been computed from a sample, what you need to do, you need to look at the differences, and as Bouba will show, for each cutoff, you can do the statistical test, and then you can also plot the band of the difference and see even if the band and the intervals they lie below 0, and then you can conclude whether it is the dominance holds statistically significantly or not. Now, there you will also find examples where curves will cross. These are M0 curves, second order dominance curves. You can also plot the head count, the survival functions, and they may cross. What can you say when they are crossing? Does it mean you just do not have anything to conclude? You can at least say, I mean, if crossing happens in ranges where you know we don't have to worry about comparisons, it's fine. What you can do sort of restricted dominance. So, suppose you look between, sorry, just lines gone awry. Anyway, so if you look at this particular band, for example, Sabina and Mariama in their paper for global MPI, they looked at pairwise or whether dominance holds, dominance between say 0.2 and 0.4. So they said, you know what, it's not only 0.33, it could be anywhere between 0.2 and 0.4, suppose. And they checked for whether the dominance holds between different pairs between that range. And they found nearly 90% or more than 90% of the comparisons actually held. Okay. So that was robustness analysis. So that was the analysis basically you conduct, you assume that your weight structure and deprivation cutoffs are given, and you look at different poverty cutoff, and then you conclude whether poverty has gone down or gone up. Then the other question is, if you are, for example, you are suggesting the central government, this is how funds should be allocated, this is the poorer region, or even you could do over time as well, but let's focus on cross-sectional things. And you want to say, well, this is my ranking, this region is poorer than that region. And then people may ask, what if you choose different weights? You face that question, right? I mean, even when in your group discussion, you had discussion about weights. Did you all agree that this must be the only weight? So even you within your group did not agree. Now, one may say, well, this is the set of weight I use and this is the ranking I get. And then you want to know, well, let's check for the alternative weight if the rankings are too different. This is a valid question, right? This is a fair question. So what you can do, you compute the M0 values or H values for particular set of weights and deprivation cutoff, and then you have 4 or 5 different specifications. You compute the M0 and H for each of these specifications, and then you compute the correlation. Pearson's correlation can be one option. If you are interested in ranks though, then certain other correlations that has to be taken into account. And let me just show you with some of the examples. And also the other motivation is that stochastic dominance conditions are definitely useful and they are powerful, because it's no matter what poverty cutoff you choose, you are going to get. And dominance, and if you do multidimensional dominance, it goes even further. It says it's not only poverty cutoff. When you are going to have robust comparison, no matter what weight you choose, no matter what deprivation cutoff you choose, and no matter what poverty cutoff you choose. Now, when you increase those specifications, of course, the number of robust comparison is going to go down. You are going to have fewer and fewer robust comparisons. So, if you do not have robust comparisons, what are you going to do? Or if you have 30 regions, please count with the combinations. How many different pairwise dominance conditions you have to do. So, in those kind of cases, it becomes very useful that you select some specifications, some alternative specifications, and do the rank correlation analysis to check if you have, if your rankings are correlated with each other or not. So, the question is, how can we evaluate the ranking of a set of countries or regions when the poverty cutoff varies, the weights vary, the deprivation cutoffs vary? So, 3 ways that you could do. You could either compute Spearman's rank correlation coefficient. I will just explain what that means. There is something, a notion called Kendall's rank correlation coefficient, and also you could look at the percentage of pairwise comparisons that are robust. Okay, so you take each pair like dominance, you take a certain range, and then you see if the comparison, each pairwise comparison, they are statistically significantly robust in that particular range. So, these are different, the 3 different. The last one has been implemented by Sabina and Mariema in their 2014 World Development paper. So, idea is that for rank correlations, the idea again is that you compute, you have an original specification, you have selected your deprivation cutoff, weight vector, poverty cutoff, you compute the M0 values across regions, then suppose you have 4 or 5 different specifications. You in your group, you already have different specifications, right? You did not all agree with the set of parameters. So, suppose you have 4 or 5 other specifications, and then you compute the M0 values as well, and then you compute the pairwise ranks and see if they are significant, if they are really highly correlated or not. If they are not highly correlated, then of course your specification is questionable. Anybody can question, well, you are just changing your parameters and everything is changing. Why should you believe in your rank? However, if you get robust comparisons, you find your ranks are almost unchanged. Whatever, or your pairwise comparisons remain unchanged within a particular range, you get really a strong sense of comparison. So, here when we are doing Kendall style, what we do for each pair. So, 10 country means 45 comparisons, 10 multiplied by 9 divided by 2. This is the, so you have 100 countries, 100 times 99 divided by 2, that many pairwise comparisons. So, Kendall's tau actually depends on the pairwise comparisons for each pair. So, the comparison between a pair of countries, so you take 2 countries, you take the original specification, you find country A has larger poverty than B, you take another specification, you find the same comparisons, A has higher poverty than B. If you have that situation, between it is called, then it is called concordant, if one dominates for both specifications. That is a concordant comparison. So, you have 2 comparisons, you have regions, suppose region A and region B. Suppose you have Punjab and Goa, the example I was giving. So, you look at the comparison between Punjab and Goa for the original specification, you see if Goa is better than Punjab. You also compute the M0 values for alternative specification and see Goa is better than Punjab. If both specifications you have the comparison in the same direction, Okay, Goa is better than Punjab in both cases, that's a concordant pair. But if you have Goa is better than Punjab, but Punjab is better than Goa, that is called a discordant specification. Okay, so they don't agree. In concordant, both agree, discordant, they did not agree. And then the Kendall tau is simply the number of concordant pairs minus the number of discordant pairs divided by the total number of pairwise comparisons. So what could be the maximum value of Kendall's tau, and when does it happen? When I have? Right, so that means both, so the regions or countries for both specifications, they are perfectly ordered. So if you have A, B, C, D, E, F, if you get the ranking A is better than B is better than C is better than D is better than E and F, and you get for the alternative specification the same ranking, A is better than B is better than C is better than D, E and F. So you have all concordant pairs, you don't have any discordant pairs, so you get C over C is equal to 1. And the lowest value? Sorry? Minus 1. That means you get just the opposite ordering. You have A, B, C, D, E, F, then you have the opposite, F, E, D, C, B, E. That means each pair, if you compare, they are discordant. So you get C equal to 0, so minus D over D is equal to minus 1. So it lies between minus 1 and plus 1. If there is independent or they are uncorrelated, you are going to have 0. So you get larger the value you get, closer to 1, stronger your sense of robustness is. And of course, there some adjustment can be found if you have ties of rank, which I mean for continuous variables, when you have a continuous, M0 can take any continuous value between 0 and 1, it's highly unlikely that you are going to have ties. But even if you have ties, it can be adjusted with a command called tau b. So in Stata, when you will be using, the command is k tau, k-t-a-u. K tau is the command to compute the Kendall's tau correlation coefficient between two rankings. And then you can specify the option tau b, which can compute the, if you have ties between two ranks, then it can compute the ties adjusted ones. The other one is Spearman's rho, which is actually more frequently used. I have seen frequently used in other branches, but I find Kendall tau to be more intuitive in that sense. The Spearman's rho, how it is computed, so you again compute two different specific ranks. So for one specification you compute the rank of certain regions. For another specification you compute the ranks of regions, and then it takes the difference between the ranks. So suppose you have 1, 2, 3, 4, 5 and you have another 1, 2, 3, 4, 5. Now you take the difference 1, 1 is 0, 2, 2, 0, 3, 3, 0. So again, if you have perfectly ordered or perfectly correlated ranks, you are going to have a value of R equal to 0 for all. And as a result, this particular correlation, Spearman's rho, is going to have a value of 1. Similarly, if you have the opposite specification, it can have a value of 0. So Ri is just the difference of rank for two different specifications. For each observation, for each region, you take the difference in ranks for both specifications, and this is how you compute. Now this is some illustrations using the MPI, the robustness to weights. So this is taken from Sabina and Mariama's paper. And so what they did for MPI, they said, you know what, suppose we have three different weight specifications. We have 1/3, 1/3, 1/3, which is the original one, but then we also want to see what if we give 50% to standard of living and give 25% to the rest of the two, or what if we give 50% to the education and then 25% each to the rest of the two. So they computed the MPIs, the M0 values for these three alternative specifications, and then they did different analysis. They looked at the correlation, they looked at the pairwise comparisons, and fortunately they found really high correlations. They found for nearly 90% or 94% of the comparisons these different rankings agree with each other. So that gives a very strong sense of robustness across countries. So this is what they found. Initially, it's from an older version. They reported both Pearson's, which is the correlation coefficient, Pearson's product moment, Spearman correlation, and Kendall, tau b, that means adjust for ties if there are any. And you can see that the correlation values, they're mostly quite high. If you have a Kendall value of say 0.9, how are you going to interpret? Remember, Kendall's value of 0.9 means proportion of concordant comparisons minus discordant comparisons, right? So if you do not have any ties, then a Kendall tau value of 0.9 means 95% concordant, 5% discordant. This is how you get 95 minus 5 equal to 0.9. So a Kendall tau of 0.9 means 95% of the comparisons were concordant, only 5% discordant. So if you have a value of 92%, say Kendall tau, then you are going to say what fraction of pairs are concordant? Kendall value of 0.92? 96. 96 minus 4 is equal to 92. So 96% concordant. So you get the sense. So in a sense, Kendall tau is much more intuitive than any other measure. But then besides rank, if you also want to correlate the values, the levels as well, of course you can compute the Pearson's correlation over there. In general, empirically, Pearson's correlation for our cases has tended to be larger than Spearman, which has been larger than Kendall. So a Kendall of 9 means it's really a strong sense of association. So for 100 and odd countries, you could see how many, nearly 5,000 pairwise comparisons, and out of those nearly 5,000, you have 95% of them concordant. It's quite a lot. And this is an example that we had from our very old paper, in 2008 paper. For the first time, we ran those Spearman's rank correlation coefficient across Indian states when you use 10 indicators. And again, we found quite a high correlation. Yes, please.
Is there a number that's more winnable? It's about 80?
Difficult. I mean, we have tried to see 0.9, as I told you, and 0.9 sort of the very high. As I told you when Sabina was talking about redundancy, that Mark McAllifrey 1992 paper with White, they used two different levels of correlation, 0.7 and 0.9 in terms of Spearman. Now, country rankings, where country rankings really matter globally, we chose 0.9 to be. If we have say 0.9 or something in terms of Kendall, we generally think it is very high and it's robust. But below that, people may question. Yeah. So I think those are the certain things that I wanted to discuss this morning. Questions? Yes, please.
Yeah. Suppose I want to study the multidimensional
Just a
poverty
minute.
difference.
Let me give you way forward this one.
Thank you. Suppose I want to study the multidimensional poverty conditions across different regions in a country. And I want to make a 5-year on 10 years data analysis. And if we are to use that, regions can be really controlled using the fixed effects, where we may not be really interested in looking at the differences, the unique differences among regions. So my question is, the examples that we have seen so far as I understand, are cross-sectional data.
Mm-hmm.
So if we are to extend this kind of application to panel and want to really look at poverty across regions, subgroups, then how are we going to tackle?
Very good question. So first of all, dominance analysis can be conducted across time. So you have the distribution of one period, you take the distribution of another period, and you see for any poverty line, poverty has gone down or not. So that you can do intertemporally. That is not only cross section. So dominance analysis, definitely you can go ahead and have you done some work in dominance over time? But definitely in an example from Duclos and Younger, when Sabina also presented, there was a map Sabina also presented that showed that how over time the difference between two planes. Remember? It was from their paper from 2 African countries, and they show that if you take the difference of these two planes in a bivariate distribution and they are statistically significantly below the value of 0, then definitely over time, with unambiguously you could say that yes, poverty has gone down. So you could do that. Whether the ranks of the regions have changed, for example, you have one ranking in this period and you want to see if the progress has been uniform or not. Okay, you can take the M0 values for one time period, you can take the M0 values for another time period, say after 10 years, and then you look at the correlation, if they are changing or not, if there is sort of mobility, if the poorer regions has become less poor and so on, depending on your objective. Of course, you can then use the same technique to look at how correlated rankings has been, or even the levels has been across these two different periods, to see if they are changing or not over time. So these analysis, of course I presented the cross-section one, but you can extend the same analysis. You can do additional analysis with panels and fixed effect. That probably takes you either for, Bouba will talk about micro and macro regressions. When you have micro regressions, you look at the micro data sets. When you have macro regressions, you can do macro panels. It is possible. But this particular analysis, yes, they can be extended to intertemporal analysis.
I know individually, it's possible to work in each year across regions, but if you are really interested in the aggregate value, and if your objective of
it's multivariate correlation, you mean?
Yeah, if your objective of study is at regional level or state level, usually you control regions by taking as fixed effects, and if you treat regions or states as fixed effects, it will be removed across time, and you will not be able to see really the differences across regions because we have already removed the variable.
Probably, I think we will have, because we'll have a chapter on regression tomorrow, because I'm not sure I'm really on getting what you are saying, because here we are just doing measurement, which is different from regression where we need to care about fix or effect. So in the measurement side, we just want to know exactly what's the level of the estimate or how to compare to region or how to compare over time. So if for some reason, let's say fixed effect reason, you get that, I mean, you will not have the ranking that you are looking for, you will get the result. You can say something that there is the comparison is not significant or one dominates the another. But here we don't investigate why this is explained by fixed effect or by any other effect. I think we'll have more clear idea on that tomorrow.
We discuss about regression techniques.
And from what you were saying about panel, the main thing is like when you want to do the dominance, you just first need to figure out what do you want to compare. So if in a panel setting you are interested in changes over time, so you don't need to care about the cross-section dimension of it, because you are comparing changes over time. If your objective is to compare the sub-region, so you don't care about, because you cannot do it at the same time, know exactly how the cross-section evolve over time. So it's really depend on what you want to compare. But what we are doing here is more measurement, comparison, And I think tomorrow we'll have more clear idea on like regression model and what's going on if we have this specification versus another one.
Yeah, makes sense. Any other questions? Very well. So we would like to see some of these robustness analysis and dominance analysis in your projects the end of this week. And now I give it to Bouba to go through the statistical inference part.
All right, so some of you were asking Bouba, so Bouba is here. So we slowly moving to post-estimation analysis. So you see, we spent like 10 days on trying to understand how we compute this and how we compute the related like MPI indices. So what we are doing from today is first, like in this session, Suman already introduced, but I'm just reminding you what you are doing. So in the first part, we are trying to see how robust are our estimates, given that all the measures and the indices that we present depend on some parameters. And Suman did it very well, so presenting the different like methods that we can use to really claim that this is our estimate. So now we'll move to another type of problem on how to draw this conclusion, which is most of the time and every time, like we use sample to estimate, because the objective is to get an estimate on what's going on in a population. But we cannot do a census to get exactly the actual distribution of the population. So most of the time, we use samples. And most of the time, the samples are very small compared to the actual population size. So how confident can we be to claim that from estimation we get from a sample, this is what we have at the population level? So this is the second type of topic that I will be presenting today. So for example, let's say we are interested in estimating the poverty level. So does the overall poverty in a country is exactly what we get from estimation from a sample? This is the kind of question like we want to provide some response here. Or let's say we want to compare poverty in two regions, and what things that what we do is just, let's say we are interested in the M0 between India and Bangladesh. So we compute the difference, but we cannot say like with full confidence that if we find that the poverty is greater in India, that this is what it is, because maybe this difference that we get is not statistically significant compared to the general level of poverty. So to be really like confident to say that, we need to do some statistical tests and analysis to say, okay, the difference that I'm getting in my regional comparison is is sufficiently large so I can say that poverty is higher in this region compared to the other one. And it could be in the analysis of changes over time. So if you compare poverty from an initial date to the final date, and we see that in the final date we have some reduction, to what extent this reduction is really statistically significant? We need to have all these statistical analysis to say, like to go and sit with our president or minister to claim with all the confidence that this is what the situation is. So basically, as I said, is how to draw conclusion from a sample to infer to the population level. So to do that, one of the most important, one of the main method or to do that is to compute what we call the standard error from an estimation. Basically, the standard error the idea is very simple. So if I have a sample, I get an estimate. Let's say someone else come later and he get another sample. He will get another estimate that may be different from the first one obtained, and so on. So if you repeat this process 10 times, 20 times, 30 times, you will get different estimates at every time. And from these different estimates, so you will have kind of distribution of estimates. And from this distribution of estimates, you will compute a standard deviation. I don't know exactly how familiar you are with with statistic and analysis of random variables. But basically, when you have a distribution, so you have like two main measures that you can compute from the distribution. The set of the first measure is what the measure of like central tendency, like means, median, this gives you a general idea. In general, this is how my population is. And at the same time, you can compute a set of measure of dispersion. So how like dispersed is my distribution. So this is just what, for those who are not statisticians, what you really want to need to understand here is like the standard error gives you the idea of how, dispersed is your distribution. So if you estimate, so you can compute, if you have like different sample, and for each sample you compute an estimate, so then at the end you will get a distribution of estimate. From this distribution of estimate, you can compute the standard error. And once you get the standard error, what it tells you is like the uncertainty related to the sampling is captured but like this standard error. So it gives you like the dispersion that you can have, the mean dispersion that you can have around your estimate. And this also like this gives you like kind of mean dispersion that you have around the actual value that you are looking for. Because when you do estimation, you are trying to estimate from a limited set of information an actual value. So that's why the standard error is a concept which is really important in statistical analysis. But the standard error is more like something theoretical and conceptual. But when you want to do more like things that you can draw conclusion from it, you compute the confidence interval using this standard error. And the idea is very simple. When you have the estimate done, we combine the estimate to the standard error to get a confidence interval. And the confidence interval tells you with certain probability, I'm sure that the actual value is inside the interval. So if you want to be confident at 95%, for example, you compute, if you want to be confident, for example, at 95%, you compute a confidence interval that tells you in 95% of cases, your actual value is inside this interval. The way to see it is, let's go back again from what I just said. Let's say you have 30 different samples, and for each sample, not 30, 100 different samples, and for each sample you compute an estimate. So what the interval, confidence interval tells you is that in 95% of cases of these samples, you will get a value that belongs to the interval. So that means more or less your estimate is with certain probability close to the actual value that you are looking for. So you see, if you have a confidence interval, you can claim with certain confidence that this is the level of poverty in this region or in this country without any risk of saying something that is not real. Any questions so far? Cool. So I have like statistician. All of you are statistician in the class. That's good. So how to compute then this so important concept, statistical concept, which is the standard error. We have two different ways to do it. The first method is the analytical method, and the second one is what we call the resampling method. The analytical method is a bit, both of them are not straightforward. They are a bit not too complex, but you need to understand what's going on. For the analytical method, the idea is first you need to understand the survey design, because what you're gonna do is just to apply the formula of how to compute the standard deviation from a distribution. But the problem, the way your survey is designed, give you, if you want to compute the accurate standard error, you need also like to, let's say, respect for some cluster, respect for maybe your survey is stratified. So at this level, what you just need to understand, I think we have in the appendix in the chapter that in the book, some formula depending on the different type of the survey, how we compute the standard error. But the main idea is we use the analytical formula, which is like the standard error is the square root of the variance. And the variance, I think some of you or all of you knows the formula. But then you match this to the design of your survey to get the real formula. For those who are interested, you will find the right formula in the appendix. The second way to compute the standard error is to do the resampling. Remember, I was just like imagining a situation where you have one sample and then you have a second sample and then a third one, and then you get the distribution of estimate. But the problem in actual life, you just have one sample. So usually what we do, you can do a resampling from the initial sample, so you construct some other sample by doing some draw. So you draw with replacement. So you draw one observation and then you replace, you draw again, and then you replace, you draw again, and then you will get another sample in that way, and you repeat this process several times, and then you get different samples, and then from these different samples you compute the estimate in each sample, and then you will get the distribution of estimate, and with the distribution of estimate you calculate the standard deviation. Is it clear? So for bootstrapping also, there are very huge literature on how to do this resampling. Do you need it to do that way or other way? What are the implications? So for those who are really interested also, you have a huge literature on that. Yes.
Should I choose one of the two methods, or can I do both at the same time? I need to understand the survey design and additionally do the bootstrapping, or just one of them?
I think if like the design of your sample is depend on how comfortable or how feasible you are with respect, how feasible is to do the analytical method. So if the analytical method is feasible in the sense that the way your survey is designed is not too complex and you can get like some estimate, so it's better to do the analytical method. Because the bootstrap, the idea of statistics of what? Because the bootstraps, a lot of people like criticize the bootstraps in the sense that you don't have new information. So you just try like to guess or to rebuild, to use like, it's like you have an orange, you press to get the juice. So at some point there is no like new juice, you just try to press the same orange. So you don't have like new information on doing the resampling, you are just trying to find a way to estimate. And I think at some point, yeah, this is also one of the beauty of statistics, so you can just like, play with some, yes, Suman or Meika or Suman. Can you help me please to...
Thank you. Please, what is the difference between the bootstrap method that you showed us now and the jackknife method?
I'm not really the specialist, so I don't know exactly what the jackknife does. Suman, do you know what the jackknife does? Or
The main idea of the jackknife, of course, I am not an expert in this field, but the main idea is for jackknife, you take away one observation randomly and compute for the rest. Then you take again one randomly, compute for the rest, and that sort of gives you a distribution.
It's related to the number of iterations.
Number of iterations.
Like in the normal bootstrap, you can do as many iterations as you want. You define that. You could say 10,000, 1,000, whatever. But for jackknife, you say you will test the total sample minus 1. So you will test, if you have a sample of 500 observations, you will test for 499 times, not taking one at a time. That's all.
So it's about just taking one away and then repeating for the rest and then computing the distribution.
so it's another way to bootstrap actually.
Another way of doing bootstrapping subsample.
Okay.
Any other questions? Yes, please.
I'm just trying to understand well the intuition of the standard error. It means after doing the bootstrapping, my standard error is going to be lower than the initial one, right?
Which
And
initial one?
when I have an indicator and I don't do a bootstrapping, I have a standard error, right? Supposedly at 0.0.
The analytical one you mean?
Yeah, exactly.
Okay.
And then I said, oh no, I want a better standard error or I have a better approximation. And then I do a bootstrapping. And then I have another standard error.
Mm-hmm.
First is, it's supposed that this standard error is going to be lower, right? That's the first estimation I did. And the second question is, why or how this helped me to what is more exact in my estimation? It helped me to be in a better interval, confidence interval, or is what exactly it does?
I'm not sure, like, because the problem with Bootstrap, you have like infinite way of doing Bootstrap. So I don't think that like Suman can correct me that the standard error that you get from a Bootstrap is better or less than the one you get from the analytical method. But it's just like different way of estimating the standard error, and I think depending on what the specific way of bootstrapping, you may get different things.
So the main difference between analytical and bootstrap, for the analytical one, you make certain assumptions. Okay, so one assumption is that you have normal distribution, you know the asymptotic properties of the distribution, which may not always be possible. Second one is that M0 lies between 0 and 1, right? When you are using analytical standard error and when you have a very low value of M0, when you compute the analytical standard error, it may be possible that they are either off the bound, and maybe inside the bound. You can even have a confidence interval if you compute using analytical standard error that you get a negative value. Okay, of course there are different corrections, but they are time consuming as well. Bootstrap, on the other hand, if you do not know, if you do not believe in those normal distribution, if you want the data to speak itself, what you could do, you can resample, okay, the same amount with replacement, and then you select all the, and you store all the points. Suppose you do 1,000 replications, and you just plot those 1,000 M0 values. And those from 1,000 M0 values, you compute sort of the standard deviation. Okay, how much they are varying. Whether standard error from Bootstrap is higher than analytical one, I'm not very sure. Okay, even for analytical one, when you adjust for the complex sample survey, the standard error may change. Okay, so if you assume random sample and then you have the strata one, because the strata one brings more variance. Okay, so in a sense, standard error could even be larger when you have complex surveys. Okay. For Bootstrap, of course, you have to take the complex surveys into account, but whether it is higher or lower than that, I don't know. Now, what we are going to do with standard error? So you have an M0 estimate, and you want to know, so you get an M0 estimate of 0.5, and you are telling your policymaker your M0 estimate is 0.5. Now it has come from sampling, and if you had done the sampling again and computed the M0, it is possible you get a value of say 0.55. Okay, so, but you cannot go in the field and survey again. It's so difficult, right? So you have to make the one sample that you have collected to speak for itself. And so you look at the variance, so you have the mean. So M0 is the mean of the CI vector. So you look at its variance as well. So suppose if you have a situation where in a country everybody is poor and everybody has an M0 value of 0.5. You have 0.5, you do not have so much dispersion from that. But in another country, suppose it varies too much. So standard error captures that, how accurately you can say that the level is just 0.5. What confidence you have to say that even if it is not 0.5, it lies between 0.45 and 0.55. Okay, so if you get a standard error and from which you compute the confidence interval using the critical value, you get a confidence interval of 0.45 and 0.55, and somebody comes and tells you, no, the M0 is 0.7. You can say, no, definitely you are wrong, because with even statistical, I've computed the statistical significance and 0.7 is falling outside that particular bound. So definitely you are wrong in that sense. So this is how you use the standard error. Standard error sort of gives, standard error is a notion of uncertainty, reliability. Okay, if larger standard error means your estimate is less reliable. Okay, smaller standard errors, that means you have a tight bound, which means that it gives you more reliability to your estimate.
All right,
Any other
thanks,
questions?
Suman. Yeah.
Question at the back. Oh, of course. You can go there and then we'll come back.
No, it's in the bottom. But
Thank you. When we are taking our sample to go to the field to collect data, we have an estimated sampling error when we are computing the sample size that we want to use. And at the point of computing our MPI, many households were dropped because they could not have data for all the indicators we are interested in. So which means the sample of households that we are using for our MPI are much lower than what we have taken from our population when we are collecting the data. What effect does this have on our competition?
Would you like to go?
yeah, first response before that the expert say something about it.
Anyway.
No, the thing is like, I mean, if you do sampling, there are two things. The first thing you need your sample to be as representative of the population as possible. So if you drop some observation, the first check that you may want to do from the cluster and stat that you use first, does the sample is still representative of the population or not? And the second thing is like, in terms of the sample size, the only thing for sure is that when your sample size goes up, the precision you get from your estimate increase. So that's the only thing that you can say. So depending on the amount of resource that you have, the ideal situation is to get the large sample possible, because when you have large sample, you have very precise estimate. So then you just then need to see what resource I have and how representative is my sample. I don't know if Suman want to add something.
Yes, completely agree with that. So what you need to do, of course, when you collected the sample, you tried to preserve the representativeness of the sample. And when you are using in the data, of course, some samples are lost. So the first thing that we are also trying to understand is with reweight the sample, because it may happen that from particular strata you have larger sample draw. So suppose that strata, particularly your households in that strata, they were representing 10% of the population, and now their weight attached to it has also gone down because the number has shrank. So now smaller fraction is still, but they're still representing that 10% of the population. So whether to reweight them, That's the first issue. And of course, if your sample size is large, and whether you would be much worried about the loss of sample size also depends on the sample size. If you have only 30 samples, we know it's a small sample size, and then if you have a loss of say 10 samples, it's a larger matter to worry about. But if you have 10,000 samples and you have say sample loss of 2 to 3%, or I mean we take a sample loss up to 15%, sort of understanding probability is not going to affect the representativeness. But since even then it is arbitrary. So if you have a small sample loss, definitely it is not, of course it will affect your standard error. Your standard errors are going to be larger, definitely, because sample size and standard errors, they're inversely related. So larger sample size you have, you get smaller standard error. So that will be reflected in your standard error. When you have loss of sample size, you will have much larger standard errors.
All right, I think we'll move, and if no, I think we are running out of time. Let's take another bench of questions later, and yeah.
I'll leave it on Bouba.
No, I mean we will have like the whole day to discuss this of if you really. So let's. All right. Not this one. So after this very huge discussion on the concept of standard error, let's see a more concrete example from a paper Sabina and Suman have on dynamic of MPI in India, where they compute also the standard error and the confidence interval. And they compute, for example, in this paper, they use the analytical method to compute the standard error. So if you want to have a close look on it, you can go and see what they did exactly. So here I will just interpret very quickly what's the interval, the confidence interval means. So you see, for example, here we have two different confidence interval, one at 95% and the other one at 99%. So let's take the case of M0. So the point estimate of M0 in case of India here is 0.251, and then the standard error associated to this point estimate is 0.0026, and from this we get the confidence interval going from 0.245 to 0.256. So this means that with 90% of confidence, you cannot reject that the actual value is inside of this interval. And with 99%, you can reject that the actual value is not outside this interval. So you have an idea like this is more or less the interval where I have for sure the value I'm trying to estimate. And you can do that at 99% of confidence. So here the level of confidence increase. So ideally, if you can get confidence interval at 99.9999%, that would be good. So standard error and confidence interval is when you try to estimate a parameters that is unknown. So you have an estimate and you are trying to test or to get an idea how accurate your estimate is or not. But sometimes you have more or less an idea on what your actual value is. Let's say, for example, a government comes and say, okay, we think that in the case of India, the MPI is 0.26. And they ask you as an expert how accurate could be this statement, for example. So you may want them to run a hypothesis test to say, okay, does this statement is accurate or not? So for this, you have the null hypothesis H0 that you said. The null hypothesis is your guess. So you guess that this is what the situation is, versus the alternative hypothesis where M0 is just different, or you may say that M0 is greater than this value that you are saying, or you may say it's less than this value that you are saying. For the first alternative, we call this kind of hypothesis test a two-tailed test. And if, let's say, you are in a case of comparing countries and then you compute the difference, you want to run a hypothesis test to see if the difference is greater than 0 or not, because if it's greater than 0, then you can say that the region, let's say I, is better than the region B, and in this case you are doing a one-tailed test. So depending also on what is the alternative to the statement or to your guess, the type of test that you will be doing also is different. But I think we don't have neither time or, not the right session to go in more detail about that. But if you are interested in hypothesis tests, also you can go in appropriate literature. So I will just tell you very briefly how the hypothesis test works. So the idea is just like when you have very large sample size or sufficiently large sample size, you know that the distribution of your estimate converges to a normal distribution. So what you have here is then in the case of M0, you will compute a statistic that usually when you do this, the hypothesis test that we call the T statistic that you compute to see M0 minus your guess divided by the standard error. I will not go into detail, but these statistics converge to a normal distribution of mean 0 and standard deviation of 1. So you will just compare the value of your statistic to the critical value that you obtain from the normal distribution, which is here Z, or Z, sorry. So if the absolute value of your statistic is greater than the absolute value of the critical value from a normal distribution, that you can reject your hypothesis. And here again, it depends on the level of confidence that you may want to have, because the critical value here depends on how confident you want your hypothesis test to be. If you want to the confidence at 99%, so the value of Z will change and so on. So that's why a similar way to do it, or an equivalent procedure to do it, is just to look also at what we call the p-value. So we'll compare just the p-value with the level of, error that you can accept in doing your test. So in one sample size, one thing which is interesting also is that doing a hypothesis test in a more formal way that just I explained is equivalent that just doing it using the confidence interval. So how you do a hypothesis test using the confidence interval, you will just try to check if my guess is inside the confidence interval or not. So let's say you have a hypothesis that in a case of India, M0 equals 0.26. You will just go to your confidence interval, check if 0.26 belongs to the confidence interval or not. If you found it inside the confidence interval, so you cannot reject that it's not the case. That's why usually, even like in analysis, we just check every time just the confidence interval and see all the value that we have inside the confidence interval. That means that we cannot reject that our actual value is equal to that value. So now, this was just like when we want to estimate just 1 point. So here, what's going on if we have like 2-point estimate and we want to compare. Let's say we have a poverty, an estimate of poverty in India and an estimate of poverty in Ghana, for example. For India, we have a confidence interval, and for Ghana, we have another confidence interval. What we can say for sure, if the confidence interval do not overlap, so doesn't mean that the difference between all the possible value, because recall that what you have in confidence interval are all the possible estimate. So doesn't mean that the difference between all the possible estimate is greater than 0. So you can claim for sure if your degree of like confidence is close to 100% that poverty is higher in India than Ghana, for example. But if your confidence interval overlap, you cannot say this does not mean also that the difference is that you cannot like the difference is not significant, because if they overlap, maybe the difference in overlapping is not significant and you still have like the dominance or not. All right, let's go back to this example that Suman previously presented, and instead of reading the standard error and confidence interval, let's see what's going on with if we want to do some regional comparison. Because I want to recall also that you can also do hypothesis to test, like if you are doing the regional comparison or changes over time, you can compute the difference and you run a hypothesis test to see if the difference is statistically significant, in a sense that if the difference is statistically greater than 0 or not. And here, this is what the statistically significant here mean. So in the case of Goa and Punjab, for example, we get the difference in their MPI is 0.31, which is statistically significant, like relatively to the level of estimate that we have. So in this case, we can say that Punjab is significantly poorer than Goa. But just to show you the importance of running this statistical test, you can see here the difference when you go from the first set of region here to the second. The difference is more or less the same, because here you have also a difference of 0.32, but this difference is not statistically significant. So if you just like compute the differences, I say, okay, it's greater than 0, so I can conclude this. So you may draw wrong conclusion. Because, so here in the second case, for example, although the difference is a bit is higher, which is 0.32, we cannot but it's not statistically significant in the sense that this difference doesn't is almost 0 from the statistical side. So if from 0 you add a confidence interval, so you will get this 0.32 inside of it. Yes.
In order to do this analysis for the overlapping of the confidence interval, to do this analysis, need I to use the same database between, one database who has all the countries, or can I use different databases and see their confidence interval, or it should be inside?
No, you can, it could be it depends on what you are comparing again. So if, let's say, you are comparing from the example that I just mentioned, India and Ghana, for example, it's different sample, different survey. So it depends exactly what you want to compare. But if you say, let's say you are comparing region of India, it's in the same survey, but the observations are different also, because observation for one region are different from observation from another region. So in any case, you have one sample here and you get an estimate and confidence interval for it, and you have another sample, you get an estimate and confidence interval, and you try to compare. But most of the time when you want to compare, so you are comparing different things. Yes?
Yeah, if you look at the NPR for the first set, it gives you a variance of 20, is it 20, 21? Huh? Goa and Punjab is 31, huh?
31, yes.
Yeah,
and
point
then
81.
Yeah, if you look at the other one, it's about 32, almost same. So why do you finally say that it is not statistically significant? Huh? Yeah.
I'm not sure I get the
The
question.
question is, you have the same difference, 31 and 32. Then why one is significant, the other one is not?
Just to give a very brief and response is like, because the value of the point estimate are different. So because the idea of like the statistical significance and standard error is meaning that you are also you are doing the analysis on relative value. So this difference is kind of relative, because remember that the T statistic, you have M0 minus your guess. So if your M0 is close to your guess, you already like close to 0 just with this, and then you divide by the standard error. So it's like you standardize everything. That's why we say, so the principle of computing the statistic is you standardize so that you can compare comparable things. So if you do all these adjustments, can tell you like, okay, finally this difference in absolute term is high, but in statistical term, which is relative term, is not high.
And the main idea is that when you get a point estimate, it is not necessary that it is going to be equally reliable across all regions. So for Goa and Punjab, probably it is much more reliable with lower standard errors, and so you get the statistically significant difference. It is possible for Andhra Pradesh and Tripura, they are not as reliable, okay? Because you will see clearly, if you look at the confidence intervals, they overlap quite a lot. 0.176 and 0.212, and the below, for Tripura is 0.195 to 0.258. So they overlap quite a lot, you see? So is that reliability factor that determines which one is, I mean, that's why you need to do standard error. So even with similar differences, it may not be statistically different, the difference.
Yeah, my question is actually on the reporting part. If you look at many publications, the statisticians would prefer to report using the values as the coefficients, the standard errors, and the confidence intervals, while economists most of the time would like to report using the coefficients, t-tests or z-tests, and the significance level, p-values. So sometimes I'm wondering if there is any difference of using this kind of approach. Basically, I prefer to report using the values and standard errors. And once you have got this, you divide the values with the standard errors, and you can really catch up the whether it is significant or no. So my question is there really any difference of reporting? This, for example, looks like a statistician way of reporting.
It's just for practical reason, because like, as you said, the things that you can read directly is standard error and confidence interval, but economists tend to present the t-statistic because this is practical reason from the programs usually that we use to compute it. You can directly have an idea of like, this asterisk and everything. So you already have the packages in your program that tell you exactly like if you get this statistic. So it's more for practical reason. That things that you cannot get from confidence interval, because when you put your confidence interval, you need to have some intellect logic to be able to read it. So but in scientific way of it is completely equivalent. So you can use one or the other one. It doesn't make any difference.
So it also depends on your objective and what you are doing. So if you have only one sample, and if you are only reporting the value of point estimate, you can either report standard error or the confidence intervals, because p-value doesn't make any sense here, right? Because you are not doing any test here, so-called. So when you are reporting just for one sample, the M0 values, report confidence intervals. Now, p-values are important when, say, what is the ultimate objective? You just want to know whether this comparison is significant or not, right? Now, if I just report 2 standard errors, or just one standard error, then you need to understand, well, this is the mean, this is the standard error, I need to divide. P-values is an easy way of representing. It does not matter what your mean values and your standard errors are, as long as you know the p-value is less than 0.05 or 0.01, you know the level of significance. So p-values is a way it allows you, so I am not saying, you know, if I have to report the significance, I have to say 95%, 1%, 90%. No, I give you the p-value and you decide what is your norm. So I allow you to choose. So I report a p-value of 0.49. Now you decide whether you are happy with that. If you are happy with 95% confidence, you say, well, I'm happy, it is significant. If you are happy only with 99.9, you would say, no, I'm not happy with that. So p-value gives you that particular power. So that's why p-values are useful in that sense. But the equivalent way of representing.
Bouba, please help me to understand. You have the MPI values, and then the standard errors and the values of the confidence interval, the lower bound, upper bound. If you take the MPIs of each of them, you see that they all fall within that confidence interval, yeah?
Of all of them. I didn't check, but I trust you, okay?
Oh, all of them. But then in the 2 last columns, you have MPI minus I, and then you have statistically significant, yeah? The MPI minus I is the difference between minus I.
It's not MPI minus I, it's actually supposed to be the difference.
Between the two.
It's just a notation.
It's for India, so we denoted initially MPI I as Indian MPI. It should be rectified. That MPI I should not be there. It should be just MPI. Please just read it as MPI.
So it is MPI.
The difference in
It's just the difference between
Between
Punjab and Goa.
Yeah, it's 0.031.
No, it's 0.031, yeah.
Yeah.
Just a
And
mistake,
the
sorry.
second one, 0.032. Okay?
Mhm.
Now, help me to understand. What does it help me to say, to reach to the conclusions you have there? That the first group is statistically significant and the second one is not. That's where my confusion is.
Okay, I think your confusion comes from the fact that here, because we are mixing, because the confidence interval here we have are for the point estimate. So it's not about differences. So I don't think you have like very direct link from, because if you want to have confidence interval for the difference, you can get it also. So this difference that you have here, you can go from M0 in, let's say in Goa, minus M0 in Punjab. So this will be your actual value that you want to estimate, which is already the difference, and you will get an estimate. So what the difference that you see here is just the estimate of that difference. Given that is just the estimate of that difference, so if you want to go on, use the confidence interval approach, so you need to compute a confidence interval for this difference. And from this, the confidence interval that you will get from this difference, you will go to the same conclusion that, this statistically significant or not comes from there. So it doesn't come from the confidence interval that you have in the left side, which are just for the single region. It's not for the differences. All right, we hope that from this session we convince you that once you get the MPI and all the indices, the work is not done. So to take things move forward, you need also to do all this statistical analysis and try to, come out with very strong conclusion without any doubt. So first, like trying to do all the sensitivity analysis, change the parameters, and see if I change this value, if I use this poverty cutoff, this deprivation cutoff, what's going on, and compute all these necessities, and then come out with very strong like ranking. And second, also see like, okay, if I have this estimate, and even for the let's say you can combine also the sensitivity analysis with the statistical inference. For example, let's say you compute the dominance curve. So the fact that when Suman were presenting, for example, he was saying like if the dominance curve do not like cross, so you have dominance, right? But to really draw very, accurate conclusion, you need also to put some confidence interval, through this dominance curve. So you will just try to see if the confidence, let's say the confidence interval behind or through this dominance curve like overlap or not. Because remember that each dominance curve is just a combination of point estimate. So for each, let's say, parameters, you have an estimate, you change the parameter, you get another estimate. So for each estimate, you can put confidence interval. So this is just to let you know that there are like couple of statistical checks that you need to do after having your estimate and move on. And then you will see how to communicate the result, the session after tomorrow, and then the post-estimation analysis that comes also on trying to understand why we get this, why not this.